This video will cover one of the biggest engineering failures in aviation history. This is the story of the Boeing 737 MAX. The 737 MAX was an improvement on the Boeing 737 series that at that point was considered the top narrow body in its class. The Boeing company had plans to develop a new aircraft with better fuel efficiency to maintain its leadership in aviation. However, at that time, Airbus launched the A320neo aircraft, which featured a new engine that was more powerful and fuel efficient than any other aircraft. So the Boeing company decided to scrap their plans to develop a new aircraft and decided to modify their existing 737s to use the newer engine that was more fuel efficient and powerful than the previous. Since the new engine was more powerful than the previous, the engineers noted that these aircraft will have a tendency to pull up its nose, which can cause an aircraft to stall. And to maintain the same flight characteristics and maneuverability of the previous 737, they decided to create a new system which eliminated the need for pilots to undergo training in the new platform. Therefore, this would give airlines a greater potential to reduce costs for training. MCAS is designed to do is to activate automatically and push the airplane nose down when it detects the aircraft nose is too high, which is the high angle of attack, or AOA, which could lead to a stall. So the sensor, the AOA, detects that the data of the angle of the attack of the aircraft is going too high and then controls the aircraft to move the nose down to avoiding stall. The MCAS only activates when the plane is flown manually, which means autopilot's off, and when the flaps are retracted and the AOA exceeds a specific threshold. A fatal flaw with the MCAS was the reason that two catastrophic accidents caused hundreds of casualties and worldwide grounding of the 737 MAX. During the investigation, it was determined that the pilots were not aware of the MCAS system and that there were issues with the software as well as to the AOA sensor installed on the nose of the aircraft. They also determined there was over-reliance on a single sensor, also engineering issues on which a lack of redundancy in the safety critical system, also excessive authority of the MCAS system, which could command significant nose-down trim repeatedly. It could re-trigger multiple times, overpowering the pilot input. And pilots struggle to counteract the system when activated incorrectly. The FAA, Federal Aviation Administration, and the NTSB, National Safety Transportation Board, helped Boeing in solving all the issues. Strategic changes in the engineering after the Boeing 737 MAX MCAS crisis. In conclusion, the Boeing 737 MAX MCAS maneuvering characteristic augmentation system disasters exposed deep flaws in aircraft design, pilot training, and regulatory oversight, prompting sweeping strategic changes in the engineering fields and aviation industries, creating the need to enhance aircraft design and safety systems. Post-accident reviews led to mandatory redesigns of the MCAS system, including some of the redundancy of one-angle VACAT sensor, reducing reliance on a single faulty sensor. Cross-FCC trim monitor to detect and override a wrong MCAS command. Updated display system to clearly show AOA warnings. Non-normal checklist to guide pilots during MCAS-related emergencies. Also, stricter certification and regulatory oversight. The FAA and other regulators reduced reliance on Boeing's own certification process, requiring full transparency of flight control system to operators and regulators, independent verification of software and hardware before certification, system safety analysis as a mandatory step before return to service of the existing aircraft, pilot training and human factors engineering, recognizing the inadequate pilot awareness of MCAS, airline and regulators implemented comprehensive MCAS training covering operations, failure mode, and override procedures, improved communication between manufacturers and airlines, and human factors reviews. Also, at the organization level, and changes in cultural engineering, providing whistleblower protections, board-level oversight, cultural shifts, as well as in creating industry-wide safety standards and protocols, with greater emphasis on fault tolerance and more rigorous testing of software and diverse failure selection, standardized safety reporting across manufacturers to prevent information silos. These changes shifted the engineering lifecycle toward proactive risk management, transparency in design, and regulated manufacturer collaboration. The focus is now on preventing single-point failures, ensuring pilot readiness, and embedding safety into every stage of design, certification, and operation. In short, MCAS disaster reshaped engineering strategy by making system redundancy, regulatory independence, and human factors integration central to aircraft safety and certification. Now, Boeing has solved the MCAS issue. As you see, MCAS was not a single flaw, but a system-wide of system failure involving lack of redundancy, underestimated risk classification, poor human-machine interface, insufficient transparency and training, weak validation and testing, organizational pressure, overriding engineering rigor. Thank you for watching. This video was created using Google Search, Copilot Search, as well as Wikipedia and other unknown sources for the photo provided.